Good day everyone, to our panelists, Mr. Jefferson Miranda, our technical and expert panelist, our chairman, Mr. Federico Nueva, and our local panelist, Mr. Randy Otero. We would also like to give our gratitude to Mr. Reggie Tan for supporting us all throughout this thesis project. So our group is group number 10 with the thesis entitled AWIT, an algorithm-focused programming language. So before we begin, let me introduce to you my fellow researchers. So first, I am Felix Jr, a student from BSCS 3A.
Hello everyone, so I'm Raffy Wamar, another third year BSCS 3A student from Pamantasan ng Lungsod ng Pasig.
Good day, sir. I'm the third member of our group. My name is Julius Mella. AWIT, an algorithm analysis focused programming language. A brief demonstration of the application. Introduction. Widely used programming language such as C++, Java, and Python exist today, which are known for very specific uses such as in the fields of operating systems, game development, or data science. These programming languages have their own compilers or interpreters while translate written code into machine-readable code. This is the same for the developers of AWIT. The aim is to create a programming language written in a native language with added feature of algorithm analysis. Objectives.
So now we'll talk about the statement of the problem. So here are our problems. First, we would like to know how to establish preprocessing of data that will allow simplification of interpretation by creating a stream of tokens. Next, we wanted to identify as well a given string of inputs to find out if it's syntactically correct as well as semantically correct as a source code. And third, we wanted to create an efficient intermediate representation of the source code in the form of a bytecode that will be processed by our virtual machine, which is represented on the fourth question, which is how we can create the machine code and create a high-level representation of it to generate the reports containing the analysis we perform on the algorithm used. Okay, so with these problems, since we are already more than 50% done with our application, there are some questions here that were already answered and on the way to be answered. So yep, these are the summary of all the questions that we have, and now we would like to demonstrate next how this application will be created, such as the summary and the grammatical rules that were utilized in the creation of that application. Alright, so now we'll discuss the contextual grammar utilized by AWIT, our algorithm analysis focused programming language, using the extended Bacchus Now form. So here it is. Okay, so first we'll just provide a basic explanation of the Bacchus Now form. Basically, this all starts with our declaration statement, which will then go on to another non-terminal statement, which is our kilalaning pahayag, which means identifier statement. Declaration on the other hand means declaration, and then it may also identify if that is just a simple statement. So next, once they find out about here, they will then connect over to another non-terminal, pahayag meaning statement, and these have several statements such as ipakitang pahayag, which means print statement, kada pahayag, which means for statement, kung pahayag, which means if statement, habang pahayag, which means while statement, grupong pahayag, which means group statement, and then expression pahayag, which means expression statement. Okay, so based on the explanation provided above, here it is. So just a basic explanation here. Kilalaning pahayag, once identified, it will connect over here. With our virtual machine, once identified, there's the word kilalaning use or kilalaning use. This only means bar in famous programming language. So once kilalanin has been used, it will then identify the word bar and then find out if pagkakilanlan o pagtatalaga was used as well. So it's not really the word being find out, but instead what will happen, this non-terminal will lead to another non-terminal which may contain this terminal or token that is identified by the virtual machine. And of course, there also must be the semicolon, which denotes the end of the statement. So yep, same idea for all the rest of the non-terminals. Once you connected here, and then yep, just like in this example, pagtatalaga, this will connect over to this one. And once pagtatalaga is was find out or was checked by our virtual machine, we must find out if the equal sign was used, which means that it will be assigned to that variable or to that bar when we use the word kilalanin. And after that, we'll find out if there's an expression used. And so we also want to discuss that this epsilon symbol means that is only optional, or that it doesn't really require the programmer or the user to use this kilalanin word, because they can also just print a statement without assigning anything. So yep, same idea for the rest of it. The virtual machine, or rather once the programmer or the user created his own source code, this will go through all these non-terminals until it finds the unique symbol or unique keyword or terminals, which will then be identified by our virtual machine and then executed into machine level language. So yep, here are some of our, or rather a summary of our extended vocabulary form, illustration of our context-free grammar. So habang pahayag, here it is. We must find out if the word habang or while was used and an expression in the statement. Yep, so in case this is confusing, it only means that while and then the condition and then the statement that must be executed, the statement that must be executed once the condition is met. So yep, here it is, same idea for everything here on the context-free grammar, especially in our paunang expression or our pre-infix, prefix or our pre-increments. As you can see here, negation, and then this for the negative or negation of the value, and then this is for negation of Boolean values, and then there's also the pre-increment and the pre-decrement. So yep, that's how it is. There's also the pagdami, which is our operation standing for asterisk multiplication, and then division for our division. So yep, all of these non-terminals here in color blue will just connect into something until they find these green colored unique symbols or keywords, which will then let our virtual machine know how exactly the source code will be used in the system, or how the machine will execute the source code. So yep, here's our lowest level of the context-free grammar. Here are our titik or characters. There's also the string, and then the numbers, the floats, and the fractions. So yep, not to mention there's also our literal numbers.
So now here we are in the image representing the modules and the inputs for those modules. Okay, so we will start here. The user will write a source code. Those source codes will then be transferred or will be inputted into the scanner. The scanner will then convert the text file or the source file from the user into a tokens. Then those tokens will then be compiled using our another module compiler. Okay, then the compiler will create a chunk of bytecodes, and then those bytecodes will then be executed inside our virtual machine. Okay, so what basically happens is that the result of the scanner will then be the input for the compiler, and then the output of the compiler will then be the input for our virtual machine. Okay, so later in our demo, and then in the next part of this, after this is the Backus-Naur form or the context-free grammar, you will see the logic behind or the theory on how this works. Okay, so basically in the source code part, the scanner uses finite state automata in the theory of language to generate tokens, and then the compiler uses context-free grammar and then context-sensitive grammar to create a chunk of bytecode, and then the interpreter will then run those instructions written in bytecode by the compiler. And finally, we are now on the demo of our language. So in this part, you will see the AWIT in action. So first, let's of course create the language. Okay, so now that we have compiled and have an executable for our language, all we have to do is just run it. Okay, so we have two ways to use the AWIT, okay, or the AWIT interpreter. First, we can just run the interpreter, and then we can type anything as long as it follows the grammar of our language. So for example, we can use ipakita to print a value, and then let's say 2 plus 4. Then end your statement in a semicolon. Then press enter. You will see the process, okay? You will see basically the stack trace of the process. So here is the stack before, or this is the picture or the illustration of the chunk of bytecodes. So we have here the bytecodes here, and then here's the stack. Here's the stack representation during the each execution of those bytecodes, and then here's the output or those for the ipakita. As you can see, this is an opcode or the operation code for print. Okay, so it prints the value of our arithmetic operation. But this actually is pretty limiting. Okay, so what we have is another. Wait lang. So this is actually pretty limiting. So what we did is that you can also run programs written in any text editor that you want, and then run it on our interpreter. So all you need to do is just run the interpreter, and then put the file Okay, put the file location or relative file location of the source file. So we have here a folder programs for our demonstration. So we have here 4 simple programs to demonstrate the features of our language. So let's start with truth machine. Okay, so truth machine is actually a simple test in a language. Okay, so what it does is that if it reads an input of 0, it will just print the input 0. But if it reads an input of 1, it will infinitely print the value of 1 until we reach the limit of our memory. Okay, so let's actually run that. So let's go to programs / truth machine .awit. Run it, and as you can see, we have here print. And if you are actually being confused of the stack execution, we can just turn that off. So we will just go to common, and then let's not define the debug trace execution, because what this does is that it it prints the stack execution of our bytecode. Okay, so let's undefine that, and then don't forget to compile it again. Then let's run it again. Okay, so as you can see, all we just have here is or are the chunk of bytecodes and then the result. Okay, so as we have in the truth machine program, if it reads 0, and then it will just print that value. But if the input is 1, then it will infinitely print out the value of 1. Okay, so now that we know that it is working, let's go into the source code to see a little about the language feature in AWIT. So first, we have here the kilalanin. Kilalanin is a token that tells the interpreter or the scanner or in the parser that we need to store a specific value given an identifier name. Okay, so identifier is actually pretty basic. You can use any any alphanumeric values as long as the first character of the identifier is an alpha character. Okay, so you cannot name you cannot name a variable starting with a number. Okay, so the variable should always start with a character or a letter. Okay, and then this one is kung. This is the if statement, and then the condition expression is enclosed in a parenthesis, and then we have here tab space to represent the scope of our statement. So if we want to use a block of statements, then we will just use a tab for that. So as you can see here in the kundiman is actually the else in our language. So else, then habang is the while. Okay, so while a is equal to 1, okay, so as long as the value or the state of a doesn't change, then we will just print the value of a. And then this ipakita a statement is actually inside the scope of this habang statement or the while statement. And then this while statement is inside the scope of the kundiman statement or the else statement. Okay, so we have here actually the ipakita actually have a depth of 2 when it comes to its scope. Okay, so now that we know that the language can use doing statements and then conditional statements, let's check another way to check or to use the conditional statement, and that is on the add even program. Add even is actually pretty basic. If the number is odd, and then we will print it is odd. If it is even, and then it is even. Okay, so we will just use add even awit. Okay, so here it says ang numero ay add. Why? Because our number is actually 13. Okay, 13 is when we use the modulo division for that. Okay, the modulo 2 for the value of 13, it will produce actually 1. Okay, therefore it will go to the else part, which will in turn print the value ang numero ay add. Okay, so meaning our language also support modulo division. Okay, so we have actually 5 arithmetic operators. They are the addition, subtraction, multiplication, division, and modulo division. Next, we will now go to basic statements. Okay, basic statements is this one doesn't use any conditional or control flow statements and looping statements, and that is the swap program. So the swap actually just swap the values. Okay, so as you can see here, what we have is actually pretty annoying to use, because what we have is that our arithmetic operations does not allow any different types of values to be computed. So if you want to concatenate, for example, a string and then number value, it cannot do that. So if we just try that here, if we add or if we concatenate the value of the number a, which is the 1, and then the string A, it will actually produce an error. So actually, the language is pretty good when it comes to error handling because it prints out the error and then the line number in which that error occurs. So if you try to run this, as you can see, this one says, inaasahan na parehong numero o parehong salita ang mga gamit. In which part? Here in the ipakita A, because we tried to add a string into a number value. Okay, so AWIT actually have an error handling and inside its inner workings, it actually have a nice architecture for handling and then recovering from an error.